Okay, now A and B are two objects on the surface of Earth, and they are feeling gravitational force of Earth as well as gravitational force between them. Gravitation is every mass in this universe attracts every other mass. This is the basic rule of this universe that every mass is attracting every other mass. But this contradicts with theory of relativity, and that is why the physics will not touch the theory of relativity. In relativity, Einstein thinks that the gravity does not exist. He does not believe in gravity, and he believes that things are attracted with one from like the force of attraction that we feel between the things is because of the space uh, canvas is bent and it is not straight around heavy masses, and that bend actually makes you feel that you have been attracted towards the center of the object. But that is not a problem right now. We will not be considering Einstein's theory, and we will be believing in Newton's theory or Newton's law actually. And Newton's law is that every mass in this universe attracts every other mass, and that includes your laptop and you. So there is a force of attraction between you and your laptop, but you don't feel that. Why? Because there's a very, very strong force of gravity that is acting on you by the earth, and that supersedes all other gravitational forces around you. But let's consider if two masses are abundant in space. They are just those two objects, and there is nothing in the space other than them. Now, what do you think will be the gravitational force between them? That will be the only gravitational force. They will be exerting gravitational force on one another, and they will be accelerated towards one another. The nuclear fusion that happens on stars is a consequence of this gravitational force, because a particle of a gas is pulled because of the gravitational force towards the center of the star, and it keeps accelerating because there's nothing on its way. It has only time that it needs. It has all the time that it needs. So it keeps accelerating. It gains a speed or gains a kinetic energy that is just enough to start a fusion reaction or continue the fusion reaction. And this is how the star keeps burning and produce heat and light. So there is Newton's law. Newton's law of gravitation. Every mass in this universe attracts every other mass. This force of attraction is directly proportional to product of masses and inversely proportional to square of distance between the center of masses. So every mass attracts every other mass. This force of attraction is directly proportional to the product of masses and inversely proportional to the square of the distance between the centers. So, and remember, gravitation is a field force. You know the difference between the field force and the contact force. Field force means a force that requires that does not require any contact. It can act with, without any physical contact between the objects, like electrostatic force or magnetic force. I hope you have played with magnets, and you must have noticed that one magnet can attract or repel other magnet even if it is not physically in contact with it. An object can fall, an object can fall without even being in contact with Earth. It means the gravitational force does not require a physical contact. So, what are the examples of contact forces that will actually help you to understand the field force? Friction, for example, tension, air resistance. These are contact force because in this case, the object one has to be in contact with object two to experience the force. But what about gravity, electrostatic, and magnetic forces? There is no contact required. So we call them field forces. And all of the field forces are sensitive to distance between the object experiencing force. If we increase the distance between the two objects that are exerting force on one another, field force always decreases. For example, if you're playing with two magnets, if you make them go apart from one another, the force of attraction decreases, or repulsion also. Similarly, gravitational force decreases if you increase the distance between the two objects. So that's why, and it also decreases with the same proportionality, same proportion. So that is why it is inversely proportional to the square of distance between the centers of the masses and directly proportional to the product of masses. Bigger the object, bigger will be its gravitational force. By bigger, I mean not bigger in size, bigger in mass. Okay. So on the right hand side, I will be converting it into a mathematical statement. This one. Uh, if this is mass 1, this is mass 2, and they are separated by a distance r meters. So remember the force of attraction between them. This is the force of attraction. They will be attracting one another by force F. This force F will be directly proportional to product of masses. So this is what it means. Force is directly proportional to product of masses. F is directly proportional to m1, m2. m1 is the mass of object 1 and m2 is mass of object 2. And the later statement, inversely proportional to square of distance between the center. This means that the force is inversely proportional to 1 over. Now, if I say 1 over, then technically I should say force is directly proportional to 1 over r square and inversely proportional to r square. So force is inversely proportional to r square. Combining these two statements, we can end up with F is directly proportional to m1, m2 over R square. Now, this is the Newton's law. And later, some other scientists, he could not figure out the constant that can make it a formula. But some other scientists, I don't remember their names right now, but they figured out the value of the constant known as the constant or universal gravitational constant. And the formula becomes F equals to capital G m1 m2 over r square, where, sorry, this is not the small g, this is capital G. G is universal gravitational constant. Its value, its value anywhere in whole universe is 6.67 into 10 to the power minus 11 Newton meter square for each kg square. So, G is a universal gravitational constant, and that is why this Newton's law is so prestigious among other laws of physics, because it is applied to anywhere in the whole universe. You can apply this law between the galaxies, like one galaxy is attracting another galaxy with the same force that we can calculate with this small formula, and a proton and another neutron, they are attracting one another because of the gravitational force as well. A proton and neutron, they cannot attract one another because of the electrostatic force, because neutron is just a chunk of mass, it is not charged. So a neutron can attract another neutron because of the gravitational force. And the formula, this formula will explain the gravitational force between them. And this formula can explain the gravitational force between one object and another object, you and Earth, Earth and Moon, Earth, Moon, and Sun. So one like Sun and rest of the Milky Way. So everything is experiencing the force, and this formula can be applied from micro to macro, any level. And this universal gravitational constant will be good for all those calculations. Now, let's move and let's find out the gravitational force between two students sitting in my class. Not obviously this class. I don't think you people are sitting close to one another. But let's see if I have a physical class, a hypothetical physical class, and I have two students. This is student A, this is student B. They are sitting approximately 1 meter away or 1.25 meter away, because we are measuring them from center to center. So they are 1.25 meters away. A weighs about 80 kg. B weighs about 65 kg. What will be the force of attraction between A and B? Can you calculate this force? So see, to find out the force between them, I use the formula Gm1 and put the values in, and the force is 2.2 into 10 to the power minus 7 Newton, which is this much, and it is very small to actually explain. Good. Now,
Sir?
Mm-hmm.
I sent you one point from the